Hi guys, cheers my products. So we've unboxed the L2 sensor. We're going to take a deeper dive. I'm going to show you some of the marketing material and some of the videos and pictures that we've taken regarding the product to help you understand a little bit better about the product. But let's just go through first and foremost what the L1 was. So we had a all-in-one device. It was one of the first of its kind. Traditionally, LiDARs were what we call radio LiDAR. So we would have ranging sensors, but spinning, right? So you would have data that would radiate outwards, something like a donut shape, right? Um, and it would be integrated and synced with an RGB camera. Um, this camera is basically taken from the Phantom 4 Pro. So we would have the same 20 megapixel resolution, mechanical shutter, and all of this will be fitted onto a gimbal, right? So at the time, it was a 3-return LiDAR, and with this 3-return LiDAR, we had about 190 meters range in real world. So that's where if you look at the bottom, the 10% reflectivity, 100 kilolux. So just a revision, uh, the reflectivity refers to how reflective the surface of whatever we're trying to measure is. So things like a freshly paved asphalt road would be 10, maybe lower percent. If you're talking about sea side, the beach sand or cement, that would be closer to 90% and above. And water would refract. So most of the data will actually be dispersed. After that, the kilolux would be the ambient light. So 100 kilolux is roughly daylight, and 0 would be a moonless night. Okay, so uh, you would see that the sensor would actually have a shorter range if it were with sunlight than without sunlight. So it's typical for LiDARs to work better at night, in fact, for that reason. Okay, it was had under the most restrictive conditions would be low reflectivity with bright ambience. You would have 190-meter range. It would have 3 returns, okay? And data would be processed through DJI Terra. Okay, it's quite a good product, but what most people wanted would be a sensor that would work better at better range. Uh, why? Because nobody likes flying too low, right? Especially if you're going areas with vegetation. What you want also would be more returns, better, which would translate to better ground level data, right? And also the software would have better features. So what some people wanted was a more integrated software environment. Of course, the RGB camera was a limitation because it had a 2-second photo to photo interval. So that limited the forward flying speed, uh, especially when we were flying lower due to this interval and the overlaps needed for the data collection. So what a lot of people wanted was a faster camera. The improvements that the sensor has now, very important, is actually uh, it has a better focus laser. All right. Uh, so if you take a flashlight and you beam it onto the ground, what you very better is if the beam were more focused. Not only would the beam be brighter, but also it would have a smaller footprint. Now, uh, when you have a smaller spot size, what will happen is you would actually be measuring uh, something more precisely. All right. This is one of the most fundamental improvements of this sensor. Now, let's just say if it had a bigger spot size, you'd be covering a lot of things and they would have different heights. So you would be having an average distance that is further. All right. So imagine if you have a larger spot, you would be measuring the leaves on the tree instead of the ground beneath the leaves of the tree. The laser also now supports up to 5 returns. And with the better focus, of course, it has a better throw, better range, right? And the point cloud data is now much higher. It fires 240,000 points a second, right? Irrespective of the number of returns. So your data is going to be uh, quite massive in that sense. So previously, if we talk about the L1, if we did 3 returns, we would actually drop the data rate from 240,000 points a second to 160,000 points a second. This time it doesn't. Even if you're doing 5 returns, it will still stay at 240,000. The camera is also now improved. It has a larger sensor. Also, it has a shot-to-shot interval of 0.7 seconds, so it's a lot faster. Now, as before, it has the 2 different scan modes, right? You have the non-repetitive scan and the repetitive scan. Okay. So one would give you a better accuracy. The repetitive scan will have a better accuracy due to the fact that it has to beam at a less awkward angle, right? That's the first thing. Uh, the non-repetitive scan will give you the most amount of coverage and the highest probability of getting targets, especially if it's small. So if you're trying to collect data across power lines and things like that, it actually has a better chance of detecting the power line. Now we've actually tried to scan this ourselves. So we've actually tried to capture the uh, laser beam image for comparison. We've placed the drone and a target. We've not changed the distance between the L1 and the L2. We've only just swapped out the sensor. And we've kept the lighting conditions constant for both. Now on the top, you can see is for the L2, the bottom is for the L1. And these are actually videos. So you can actually see sometimes in some of this, the beams are moving. Now the first big difference is the intensity of the laser beam of the L2. As you can see, it's a lot brighter for the L2 compared to the L1. Number 2 is the focus is better. It's a much finer line. Not only is the line finer, but the spacing between the lines is smaller. And it's so fine that you no longer see the gaps between the individual beams that are fired up to the surface. So what this means is you get better data because it's a tighter data set. The measurements have less gaps between them. So again, this is a rough animation of how the 5 laser returns affect your data collection. Now later we will be doing a comparison from actual data collected, so you can see how it actually differs. So if you had a fine thing like a power line, it would be about 1 to 2 centimeters wide. If your laser beam hit this power line, and this 2 centimeters would only reflect 15% of the light that was shone out, it would not be detected as a return because the return is weak. Now that you have a smaller beam, uh, the energy of the beam that is reflected by the same surface of the power line is greater. So it would increase the chance of the power line being detected. It's not that the laser is not shone onto the uh, power line, but it's a matter of how much is reflected, detected by the receiver, and recognized as a target. by the system. So a smaller laser beam not only penetrates better, but it also reflects better. So that is why you would have a better chance of collecting data from smaller targets. Another criticism of the L1 was the requirement of warm-up time for the IMU. So if for those who have never used the L1, you would have, when you first turn the system on, you would have to wait for the IMU in the L1 to warm up. It could take anywhere from 2 minutes to 5 minutes, maybe even 10, right? And that would be a waste of battery, first of all. And second, it would eat up time, especially if we were doing a corridor mapping, because you would have to move very frequently. And every time, if you had to power down and move, what will happen is you would have to wait for it to warm up every time you power it up again. So that ate significantly into work time. With the L2, you no longer have to wait for it to warm up. The system has its own temperature control. Second is the calibration will already fix this problem in the air, so you don't have to worry about warm-up time. So the camera on this guy is a 4/3 inch CMOS, 20 megapixel with a 200,000 mechanical shutter lifespan. Essentially, it's the camera from the M3E, right? The wide angle camera from the M3E. So you have uh, everything that that camera can do, including the 0.7 second interval shooting. The only thing is that it doesn't do your smart oblique, okay? Um, but other than that, you get the same uh, focal length, the same speed, and the same good quality pictures from the sensor. One net effect of all of this with the stronger beam is that A, you can fly higher, which increases the swath width of the data collected. Number two is because the beam fired at a higher rate this time compared to the previous sensor, you can fly faster and still get similar uh, points per square meter, right? So we will show you how that is with a side-by-side comparison data later. So this is what the solution looks like. As before, you would have to do your mission planning in the Pilot 2 app. The drone, it doesn't have to be an M350 RTK. You can use the M300 as well, but you have to use it with the RC Plus, which is the remote you see here on the left. Okay? It must be with that remote. So you'll have to do the firmware change, those that start with the 7 for that reason. Okay? So you would have the RC Plus remote running Pilot 2 app, running on the M300 or the M350 drone. You would have the sensor, the L2, and data processed by DJI Terra. In the box, detail is you will get the sensor. Standard, you will get a 128 gig micro SD card. You get the same hard case, lens cloth, user manual, Terra, a product certificate, and some desiccant. So just a quick comparison. If you look, first of all, the efficiency part, you will fly higher, you will cover more area per flight, and because it's a combination of a higher flight and higher flight speed as well. The L2 supports 5 returns as opposed to the L1 with only 3. The sensor at single return is the same 240,000 points a second. With 5 returns, you multiply the number by 5, you would have your 1.2 million points a second, the L2, whereas the L1 will only have a maximum of 480,000 points a second at 3 returns. Okay. Another thing more important to note will be the results, the accuracy of the sensor. It's a lot better now because of the more focused beam and the smaller spot size as well. So the additional benefit of having a more focused laser, you can operate under the same 10% reflectivity 100 kilolux environment at a higher altitude. The additional function of having a laser rangefinder with the L2, the field of view is roughly about the same for both. No more warm-ups, and you would actually have a longer uh, automatic calibration interval. So one of the new benefits of having the new IMU is that previously you would have to have a calibration every 100 seconds. If in automatic, it will still maintain that way, but when manually flying, you can tap the calibration function once and wait another 200 seconds before your next calibration is necessary. Of course, again, with the newer IMU, you get your better accuracy, as well as your new camera will give you not only a longer lifespan, faster sensor, and also it would help with the uh, point colorization. Some of the new features is that with the L2 is that you can now see not only, so previously after one flight mission, you wouldn't be able to see the collective point cloud of that flight. Now, not only can you play it back and see the final product, you can also have uh, multiple flight routes stitched together, so you can have a overall larger point cloud. Another handy tool is that at the end, there's a field quality report for each flight, so you will know whether you will need to post-process anything else or have additional base station data to perform the PPK.